Alright, welcome to the stream, guys. How are you all? So let's start where we left off in the last stream. I think we reviewed the slide up to this point, so let's continue from this point onwards. Alright, object construction, the big picture. Okay, we have a caller and a callee. So in case of caller, we call the constructor. So what happens? Okay, we assign the base address of that particular object in P1, and so the assignment of memory occurs on the callee side, but on the caller side we just get the return base address as a returned value. So in this case we get 6012 and we assign it to P1 variable. Okay, this is the pseudo code. So push 2, push 3, which are the arguments, and we call pointer new. After that we pop that value into P1. The value which was popped is the return address, not exactly the return address, the base address of the returned object. And we also create the symbol table. Yeah, the compiler updates the subroutine symbol table. During compile time, the compiler maps P1 on local 0. Okay, P2 on local 1. Yeah, I know about it. D on local 2, which are the three variables during runtime. Okay, during runtime, the execution of the constructor's code affects the creation of the object themselves on the hill. Okay. So yeah, the creation of objects happens during runtime. So that's when the value is returned. Okay, now let's review the callee side. When we call the constructor, which is new in this case, what happens? The constructor must create a new object. Just like any method, the constructor must be able to manipulate the fields of the current object. Yeah, alright. In case of constructor, the current object is the newly constructed object. Implementation, the compiled constructor code starts by creating a memory block for the representing the new object. Sets this constructor code can access object field. Yeah, right. Or the constructor, not the constructor, the class. This class as well, we have an object label, not an object label, a symbol table. We have xy point. Okay, compiling constructors, the compiled constructor code. The compiler creates a subroutine symbol table. All right, push argument 0, push this, pop this 0. Okay, push argument 1, pop this 1. Okay, I got it. What do we do after that? Push static 0. Yeah, because static, okay, the class level symbol table and the constructor level symbol table. Pop static 0. We store the value in point count. Okay, after that we have to return this point, push pointer 0. Wait, why are we pushing pointer 0? Oh yeah, we have to return this in this case. Yeah, so this contains the base address of the newly created object. That's why we return this, right? Yeah, compiling constructors. Okay, let's now see the manipulation of objects. Is my freaking internet down again? Let me check. The hell? Downloading speed is very low. I hope that uploading speed is okay, or else the stream will crash. Damn, even the downloading speed is down. No, I don't think so. It seems alright, I guess. Okay, it doesn't matter. Let's continue. Yeah, so where was I? Manipulation of objects. Caller, callee. Compiling method calls. P1 distance. So this is the method call. P1 distance, P2. Okay, what happens when we call a method? What the hell is this? Source code, object oriented, target code, procedural. Yeah, alright. The target language is procedural, therefore the compiler must generate procedural code. Yeah, right. Solution: when calling a method, the object on which the method is called to operate is always passed as first implicit argument. Yeah, alright. So we pass the object as the first argument. Push object, push x1, push x2. Okay, and then we call hmm. I think we also need to pass the argument, the number of arguments. Yeah, we do have to pass the number of arguments. Generated, this is the generated PM code. Yeah, push P1, push P2, call distance, and pop it into D. Method distance. Methods are designed to operate on the current object. Yeah, this therefore each method's code needs to access the object's field. It does it by using this pointer, right? The method's code can access the object's ith field by accessing this I. Okay. To enable this, the method's code must anchor this segment on the object's data using pointer. Oh. I'm still unsure how we are going to create the symbol tables. Not how, but when are we going to create the symbol tables exactly? I hope it gets cleared as we read on. Next, it generates code that associates the summary segment with object. So first we push argument 0. Okay, because argument 0 contains the object's base address on which we are operating. We pop it into 0. Into 0. Now what is at push? This 0, this 0, I think it is X. Let me see. First we do push this 0, then we push argument 1. Oh, why do we do that? What is that argument 1? We have other. Oh yeah, I get it. This 0 points at X. Yeah, and after that we push argument 1, which contains others address other, and we call point dot get X. Okay, and we push one argument from stack. After that we do subtraction on both of these values, and we pop it into local 0, which is mapped at dx. Similarly we do for dy is equal to y minus whatever. Similar code. Okay, return, and now comes the return part. First we push local 0, which is what, dx. We push it twice, then we call multiply, and we push local 1 dy, push it twice, multiply, add them up, call square root, and return the value. Right. Hey Detox Mango, how are you? What's up, man? Well, it depends. Are you downloading malicious software from the internet? What operating system are you using? Are you using Linux or Windows or Mac OS? Yeah, right. Windows. I mean, for Windows, the chances are much higher than Linux. But if you don't download anything from malicious sites and don't open any, suspicious links, then you will be okay, I guess. Even when I was using Windows, I didn't use antivirus. I was just using the basic Defender. So because I was not downloading software back and forth. Pirated word. Well, it depends. Well, if you are already using a pirated software, then pirated software is basically a software which has been cracked open. So there are chances that a pirated software contains virus, because that's what the pirates do. I mean, they can create a backdoor in that pirated software. But you will be all right mostly. There are ways you can check if there are malicious software on your PC or not. And if you say you are using a pirated word, then chances are you have cracked it using KMS, I guess. It's a software to crack Windows as well as Microsoft Office. So yeah. But I don't think you might be infected. And there are ways you can check if there are any outgoing connections from your PC, like if there is a backdoor or something which sends data or connections back to a server. So you can check that. Macros. What kind of macros are you talking about? Word macros. I don't know. I mean, are you saying that macros allows malware to get into your PC? Because I have not used macros. I mean, if you are not downloading anything back and forth, then you will be all right. You don't allow macros. I mean, I have no idea what a macro is, but yeah, there are many ways to, but it's pirated or open source software for PDF. Yeah, I mean, if you are using an open source software, then you will be all right, because those don't contain malware mostly, because many of the people have reviewed those code. So you will be all right if you're using open source software. But pirated, I mean, there are chances that if you're using pirated version like cracked games and so on, then there are chances that you might get infected, or you might have been already infected if you have already downloaded OpenBS. Yeah, I mean, nothing is secure anyway, but yeah, I mean, if you talk about that kind of things, then it falls into privacy category, not exactly malware and such, but there are always chances that this kind of organizations are spying. Like even using a Tor browser is not that secure. Just this morning I was reading that many of the exit node of Tor were, hijacked, and people were downloading the history and so on, attacking the exit nodes. So nothing is secure anyway. But if you don't download any pirated software, then you will be alright. Like chances of getting malware on your system is very much low. But yeah, there's always a chance that these organizations are spying on people. So yeah. Have you watched the documentary on Edward Snowden? What was it called? Do you know who is Edward Snowden? Well, my internet is a bit down. Citizen 4, yeah, there's Citizen 4, and there's also Snowden, I guess. Snowden movie. Compiling void methods. Yeah, this is the caller's code and the callee object. Print. Void print. The compiler constructs the method symbol table. Okay, no code is generated. Next, it generates code that associates this memory segment with the object in which the method is called to operate. Okay, we pass P1, I guess. Push argument 0, and we pop it into pointer 0, which assigns the value to this and the usual code, and after that we push constant 0 and return if the method is that the return type of the method is void, then we push constant 0. Okay, what after that? Call is contract. Before terminating, I must return a value. By convention, void methods return 0. Okay, and caller's contract. After calling the void method, I must dump the topmost stack value. Dump yeah, I mean, if the return value is expected, it is dumped in a variable or something. Yeah, right. Okay, now comes the part where we handle arrays. Okay, this is how we create an array. First we declare, or what is it called, define. Is this called a definition? Yeah, I think this is a definition. Or is it a declaration? Yeah, so this is how we declare an array, variable array, and we call array.new file. Generates no code, only affects the symbol table. New and is the number of or the length of the array. So array construct. Who did the malware? You mean who create malwares? People who create malwares and stuff? I mean, you know, when you talk about NSA and a backdoor in BSD, that's not exactly a malware. It's a spyware. So those are two. I mean, they are basically, I mean, same a code which is, you know, running behind the eyes, as it were. But the purpose of both of this code is, I guess, different. But yeah, there's not much difference. So, I mean, yeah, there are people who write malwares, or you know, there are people who, I mean, there are jobs directly related, I mean, specifically for malware analysts. So they, you know, unpack this kind of malwares and try to trace it and all of those stuff. Two portable virtual memory segments that can be aligned to different RAM addresses. Oh, yeah, okay. This points to object presents the values of current object and used to represent values of array that points to an array. That pop pointer 0, pop pointer 1, sets this, sets that. ZeroDays for malware. Yeah, I mean, so ZeroDays. I mean, if you are cracking a software, then you find a world. So suppose, let's say, there's this browser, Brave browser. So if someone, let's say, suppose that this browser is not open source, I mean, not freely available, like you have to pay for it. So if someone tries to crack this software and puts it on the internet for people's use for free, right? So I mean, you don't know if that person only cracked it or also, you know, injected some malicious code that will, you know, talk to their server and send data and all of those things. So I mean, to even to crack this software in the first place, they have to find a particular vulnerability. I mean, if that vulnerability is not known by the developers yet, then I think it is called a zero day, right? Zero day vulnerability. So yeah, even for malwares, so that's how you can, I mean, suppose there was a ZeroDay in a Windows OS and nobody knows about it, then you can create a malware and spread it through, and until and unless that vulnerability has not been patched, or the developers don't know about it, then it is called a ZeroDay, and you can create a code that will exploit it. So that's basically what, well, that's not exactly a malware is a software that is injected. There are a little bit technical differences in all of these terms. I mean, if you have watched that movie, I forgot the name, but it was I think, biggest cyber attack or something. Not biggest, but what was it? Let me Google it. Cyber attack on, was it Iraq or Iran? Iran nuclear plant by NS. Stuxnet, yeah. So this was a kind of a malware that was created by NSA, Stuxnet, and they exploited the ZeroDay's vulnerability in the microcontrollers of the, what was it? I don't know exactly the term, but penetrates Windows vulnerability malware that used Windows vulnerabilities to penetrate the SCADA. I think this is a system SCADA which controls the the nuclear power plant cooling and all those systems. So yeah, this Stuxnet malware was exploiting the ZeroDay vulnerabilities in this particular hardware, or was it software? Exactly what this is, SCADA. But you can watch this documentary. I forgot the name, but they have demonstrated all of these things, like how was this Stuxnet malware created, and why was it created, and all of those things. ZeroDay, I think the name is ZeroDay or something. ZeroDay. Yeah, I think it is ZeroDay. Is it ZeroDay or ZeroDays? Yeah, it is ZeroDays. It's all about this Stuxnet malware. So if you are interested, you can check it out. RAM access using that. Okay, that stores the base address. Wait, does it store the base address? RAM 805617. So how do we access RAM 8056? Well, we push this value and we pop it into that. Now we can push the 17 on stack and pop it at that 0. But this is not the right way, I guess. So we use offset. We get the base address and we add it to the offset. We add offset to the base address to access that particular index. and we pop it into that, push 17, pop that 0. But again, this is not the correct code. Yeah, what we should be doing, I mean, it will fail, this code will fail for this case where we have, we are assigning one indexed value into another indexed value. So when we use this code for this operation, it will crash because we are overwriting the previous data. So for that we have to use a temporary variable. So how do we do that? First we push A and push I, push A and I, we add it, then we push B, J, edit, we pop that one. So B is the base address of this array B, we pop it into that pointer one. So now that points to that particular value, we push that value in the stack and we pop it into a temporary variable. After that we pop this value, addition of this value into pointer one, we push it again into, yeah, we get the value from temp again, we pop to that 0. Yeah, that's how we assign. Array access, general solution for generating array access code. It will handle this what is it called, recursive accessing as well. Great, so we have seen all of this. Now the big picture. We are almost at the end of the slides. Classes, function, constructor, methods, arrays, objects, map on. Standard mapping on the VM specifies how to map the constructs of a given high language on the constructs of the virtual language. Files and subroutine mapping. So for foo.jack, we'll have the corresponding foo.VM, which will be generated by our compiler. Right, for the constructor we will have this kind function, yeah, function code, the function foo.bar, function foo.base. Each file name.jack is compiled into separate file VM. Its subroutine in this file, subname in file is compiled into a VM function, file name.subname, file name.subname. Okay, a constructor, a jack constructor function with key arguments is compiled into VM. Okay, for constructor we have key argument, but for method we will have key plus one arguments. This one argument includes the pointer to that particular object on which we are operating. Right, variable mappings will have local variables, arguments, static and field. Local variables are mapped onto local, okay, and argument variables are mapped on the virtual segment argument. Static, the static segment and field, Yeah, it's on the heap. The field variables are on the heap, right? Yeah. Alright, I gotta go to the bathroom. I'll be back in a minute. Array mapping. Accessing array entries. Access to any array entry as I is realized as follow. First we set pointer 1, okay, to the entry's address AR plus I. Access the entry by accessing that 0. Good. Compiling subroutines. When compiling a jack method, the compiled VM code must set the base address of this segment to argument 0. Jack method. Okay. When compiling a jack constructor, the compiled VM code must allocate a memory block. Yeah. Then set the base address of this segment to the new object's base address. The compiled VM code must return the object's base address to the caller. When compiling a void function or void method, the compiled VM code must return the value constant 0. Okay. Compiling subroutine calls. Subroutines and subroutine calls. The caller a VM function must push the argument 1120 stack and then call. The call subroutine is a method must first push a reference to the object on which the method is supposed to operate and then call the method. If the subroutine is void, must pop and ignore the return value. Okay. Compiling constant. Null is mapped on the constant 0. False is mapped on the constant 0. Okay, null and false, both of them are mapped to constant 0. And true is mapped as -1. Okay. First we push 1, then we do neg operation. With classes and subroutine with return in jack, implemented a set of 8 compile jack classes, math, memory, screen, output, keyboard. Okay. Any VM function can call any OS function for its effect. Oh. So, alright. The 8 OS VM files must reside in the same directory as the VM files. Multiplication is handled using method multiply, division using method divide, string constant, string new. Requires allocating space for the new object using memory alloc, and object recycling, memory realloc. Okay, finally we are at the proposed implementation. It gets boring when you are not writing the code. Compiler development roadmap. Modules. We have jack compiler, topmost main module. Jack compiler. Jack tokenizer, symbol table, VM writer, generates VM code, compilation engine, recursive top-down compilation engine. For each jack file, the compiler creates tokenizer and an output file. Next, the VM compiler uses the symbol table compilation engine and VM writer controls to write the VM code into the output file. Okay, tokenizer already developed. We have symbol table, can be implemented using 2 hash tables. Yeah. Each variable is assigned a running index within its scope, table and kind. The index starts at 0, increments by 1 each time a new symbol is added to the table, and reset to 0 when starting a new scope. Wait, what? Okay, so scope is defined by kind. I see. Scope table and kind. Oops. Oh, I will have to reload the slides. Am I online right now? Or did it got disconnected? It seems unstable. Let's just wait for stream to get stable. I think it got stabilized now. Nope. Internet is very shitty right now. Getting like 400 kbps downloading speed, and the uploading speed is fairly well, but still the stream is a bit unstable. The hell with it. Let's just continue. It doesn't matter, we are not writing the code anyway right now. Whoops, what happened? Yeah, I have to go to the 91st slide. 91. When compiling an error-free jet code, its symbol not found in the symbol tables can be assumed to be either a subroutine name or a class name. Okay. Other than keywords, right? Good. Got it. Finally, we are at the API stage. We have the API for symbol table. We have constructor, creates a new symbol table, starts subroutine, starts a new subroutine scope, that is resets the subroutine. Okay, now I'm not really sure how we are going to handle symbol table. I mean, at what stage are we going to create a symbol table and so on? Define name, the class name, type, kind. What does it do? Defines a new identifier of the given name, type, kind, assigns a returning index. Static and field identifiers have a class scope, while arg and variable identifiers have a subroutine scope. Okay. Variable count. Kind of. Variable count. Kind of. We pass the name, it returns the kind of that variable. Okay, this is alright. Type of string, index of, and returns the indexed. Then we have VM writer. We already have another VM writer. Do we need to modify anything in this VM writer? Yeah, in this case now we're going to create a vm.vm file. Wait up. Yeah, we don't have a VM writer. We have compilation engine. Gets its input from the tokenizer and writes its output using the VM writer. Okay. x-axis is part of an expression. What is x-axis? Oh, if x-axis is part of an expression. Okay, then we have the compilation engine. Same as in project 10. Extends the syntax analyzer into a full-scale compiler. Syntax analyzer done. Symbol table handling, yeah, that's what we have to create now. And the stage 2, in the stage 2 we have to write the code generation code. That's meta. I like meta level stuff. Yeah, so let's see the creation of symbol table output of the syntax analyzer. This is the output of the syntax analyzer. Good. Extend the handling of identifiers. Okay, so do we have to extend it in the symbol table? Oh yeah, we have to extend the syntax analyzer. And in the final code generation step, insert the VM code, focusing on the two instructions highlighted in red. This is a quiz. Okay, so now we have reviewed all the slides. Let's try to implement the stuff now. Right. Should we try to implement it in the stream? Because my internet connection is a bit low today. Let me recheck it again, and then we'll get started with writing the code. Okay, yeah, I mean, it's not that bad. So let's start writing the code. Okay, it's saying that we have to extend syntax analyzer. First of all, let me open a duplicate tab. Yeah, right. So we have to extend the syntax analyzer with the identifier handling described above. Okay, let's review the API of symbol table. Yeah, we need. When should we call the symbol table? Create a tag for index. Okay, let me try to think about it. So we have hierarchical XML code as output right now, and we have to convert it into the equivalent VM code, right? So how do we take this input and convert it into VM code? All right, so first we start compiling, we tokenize it and we pass it. Okay, let's see. Compiler uses symbol table compilation engine and VM writer modules. Alright, so what does the compilation engine do? I mean, tokenizers. The compilation engine creates the hierarchical structure. Alright. What's the use of the symbol table? When should we create it? Okay, yeah, so it's just a dictionary. So when we open a particular file, let's say this file, we create a symbol table. So this symbol table is for the whole class level symbol table, right? So we have field for this variables x, y, the class level variables, which are of two types, two kind, field, either field or static. Then we have subroutine level symbol tables. Now this is confusing. When should create a subroutine can be implemented using two hash tables? Yeah, I mean, when should we create subroutine symbol tables? When we come at this point, when we have to compile this, right? Yeah, start subroutine. Wait, so whenever we come across, when do we call this start subroutine? When we are compiling? Yeah, I think so. When we compile, define. Return defines a new identifier of the type, name type at kind, and assigns it to a running index. I have not symbol table. Yeah, so let's say in symbol table we create two hash tables for this symbol. What should we call the first one? Class level symbol table. Self dot class symbol table. Class st. This will be a symbol table. What should be the structure of the symbol table? Name type kind. Should we create an array of symbol tables, or I think we should create an array of symbol table, right? No. Oh yeah, so let's create a symbol table for which the keys is the name. Yeah, key is the name, right? The key is the name, and type kind and hash are the sub hash table. So it will be something like this: name and type kind and index. right? It will be of this kind. Oops. Right, that's correct. Okay, so let's create two symbol tables. The second one will be, yeah, what should we call it?